Hi everyone, in this video we would be designing the ride sharing system which is generally asked to experienced candidates. So let's get started. First, let's try to understand the entire flow which we would be designing. So whenever you will be opening your Uber application, the first thing which you have to do is enter your source location and the destination location. On the basis of this, you'll be shown this page wherein you'll be able to see the vehicles and their pricing. For example, here Uber Auto is charging me 450 rupees and Uber Go is charging me 600 rupees, right? So after seeing the pricing, you'll be selecting a specific vehicle, right? For example, here I selected Uber Go, and after selecting, I'll be pressing on this button. So once I press on this button, I'll be redirected to this page wherein I need to select a pickup location and click on this button. So once I click on this button, a driver will be assigned to me. Okay. So this is the entire flow which is used in the Uber application. So what Uber does is Uber has created 3 APIs in order to go from one screen to another screen, right? So let me show you that. So these are the APIs which are used by Uber. So the first one is estimate price. So on the first screen, you need to enter the source and the destination, right? So on the basis of that, you will be getting a product to price mapping. Now, what is this product? So what Uber does is they refer their services as product. So for example, Uber Black, Uber Share, Uber X, etc. are the products. They are not the vehicles. I'm highlighting this stuff because there are two things in my design. The first is product, which is the service provided by Uber. And the second thing is vehicle, which is the actual vehicle owned by the driver. Okay, so these two things are different. Don't get confused between them. Right. So once you call this API, you'll be getting a product to price mapping. Right. Now you'll be selecting one of the product, right? So once you select one of the product, a fare object would be created. Now what is this fare object? So for that, let's try to understand a scenario. So let's say at 12 p.m. you decided to go with Uber XL option because the pricing for that was only 500 rupees, right? So you selected this Uber XL and went to the next page. But let's say after 30 seconds, the price went up from 500 rupees to 600 rupees. Now, what should you be charged? Should you be charged 600 rupees or 500 rupees? Obviously 500 rupees, right? Because while selecting Uber XL option, you saw 500 rupees, right? So that's the thing which we are going to deal with. So once you select a particular product, a fare object will be created which would store the pricing while selecting a particular product, and that fare object would be locked for certain time duration. Uber basically locks that for 2 minutes, okay, and after 2 minutes it will throw this exception. So that is the same thing which we will try to do. So we'll be locking that stuff for some seconds. I am locking that for some seconds because I need to show you the demo, right? I'll not lock for 2 minutes. Let's say I'll lock for 5 seconds. Okay. So we'll lock that object for 5 seconds. And if someone tries to book within that 5 seconds, they will be charged the same amount which they saw on the previous page. Okay. And if they try to book after 5 seconds, I'll be throwing some exception, right? Now this verification step is done while requesting a ride. So in this API, what you have to do is you need to pass the fare ID and the product ID and the source and the destination location, because the same thing is done by the Uber. You need to pass the fare ID and the product ID and the start location and the end location. So we'll do the same thing. And over here, we'll first check whether the fare ID is expired or not. If it is not expired, we'll be trying to assign a driver which provides this service. Let's say I tried booking Uber XL, then I'll be finding a nearby driver who provides Uber XL service, right? So this is the entire flow which we are going to be designing. And in order to design that, I will be implementing these functions. All right. Now let's try to formally write all the requirements on the basis of our understanding just now. So firstly, I have divided this requirements into three parts: dynamic, extensible, and concurrency. So in the dynamic, the two things that rider should be able to do is, first, the rider should be able to view the prices of all the products. Second is rider should be able to select a specific product and request a ride. So these are the operations which rider can perform. Now coming to the extensible category, the two questions that you can ask the interviewer is, first, is there any specific pricing calculation logic to charge the driver? So let's assume that interviewer says that currently our system has only one pricing strategy, which is night based pricing. That is, during the night time, the rider should be charged extra, right? But this thing should be extensible. That is, in future, I should be able to add different pricing logic without modifying the existing code. And the second point is, how should we assign the driver to the rider? So let's assume that the interviewer says that currently we should be assigning the driver based on the rating or based on their nearest location. So on the basis of that, a driver will be assigned, but in future we should be able to add different assignment logic as well. So both of these points are indicating us to make our system extensible. Now coming to the third category, which is the concurrency, here we have to deal two things. The first is, let's assume that there are two riders who are currently in the same location and trying to book a ride, and there is only one driver available in that location. So obviously that driver should be assigned to only one rider, isn't it? So we have to make sure the same driver is not assigned to two different riders simultaneously. Okay. And the second thing is, while booking a ride, we should be checking the fare ID, whether it is expired or not. If it is expired, that is, if it exceeds this TTL, then we should throw the exception saying that fare is expired. Now please go back and select a vehicle again. Okay. So I hope now you understood all the requirements. So on the basis of this requirements, let's try to come up with entities and the relationship between those entities. And finally, we'll be seeing the entire flow of our Uber application. All right. Let's try to understand each and every entity present in this diagram and finally understand the flow of this diagram. So let's start with the models. So this is the ride class, and each and every ride would have the ID, the product which user has selected, for example, Uber XL or Uber Auto, etc. The source and the destination location, the rider himself, the driver who is assigned to this ride, the vehicle of the driver. Okay. And I already told you that there is a difference between the product and the vehicle. Vehicle is the actual vehicle owned by the driver, and product is the service which is provided by the Uber. Okay. And finally, we have the status. So whether the ride is in requested state or accepted state, or you can say started or completed, right? These are the different status of the ride. And this ride has the object of rider, isn't it? So there is one has a relationship between ride and the rider, and each and every rider would have their name and the ID. So it can have more stuff, but right now for our design, we only need these two. Then ride also has the driver. So driver will have the ID and the name, obviously, and driver will also have the current location. We need this current location so that I can get all the available drivers who are nearby the source location. Okay. So that's the reason why I need the current location for the driver. And driver also has this available atomic boolean variable. I'm making this variable as atomic boolean because I don't want one driver to be assigned to multiple riders, right? So that's the reason why I have this atomic boolean variable. And obviously the driver would be having the vehicle. So there is one vehicle object and the rating. And apart from that, it has two functions. The first one is available in order to check whether driver is available or not. Second one is to mark the driver unavailable. So this mark unavailable operation is atomic in nature. Why it is atomic? Because I will be using the compare and swap technique in order to convert it from true to false. We'll see that in code. And the driver would be having the location, right? So location is represented by latitude and longitude. And driver will also have the vehicle. So vehicle will have two stuff. The first one is the number plate and the second one is the supported products. Why list of supported product? So for example, let's say there is a driver who has a car. It can be any car, but that driver can use that car for various Uber products. For example, Uber X, then Uber Share, then Uber Pet, etc. So these are the various products for which a same vehicle can be used, right? So that's the reason why one vehicle will have list of products. Okay, and I have made one product interface which will have all the common attributes like ID and the type. Apart from that, we have various classes or various implementation like Uber Auto, Uber Go, Uber X, and each of them would have their own base rate, per kilometer rate, and per minute rate, isn't it? And in future, if I want to add more stuff, I can directly add that into their respective classes, right? And since this product has the product type, so there is one has a relationship between this product and the product type. This product type is nothing but the enum, wherein all the different types of products would be listed. Then we have this fare object, which would be locked for certain time duration. Currently in our system, I have locked this fare object for 5 seconds, after which the fare ID would expire. So this fare object has ID, the product which user has selected, the source and the destination, and the actual estimated fare. All right. And I also have this created at variable. I'm using this because I want to know whether the fare object is expired or not. Okay. So these were the models. Now coming to the fare estimation service. So fare estimation service would have the fare repository in order to store the fare objects. And it will also have the pricing strategy so that we can calculate the price for a specific product. In this service, we have couple of functions. The first one is get fare estimates. This function will be returning us the product to price mapping. Okay. So this function will be basically using the pricing strategy in order to calculate the fare. We'll discuss that in a moment. And we also have this create fare function, which will create the fare object and lock it for exactly 5 seconds. All right. So before checking out this pricing strategy, let me show you one more stuff. Now for each of these classes, we have to first calculate the base fare. This base fare is nothing but the addition of these three parameters. The first one is the base rate. So let's say you book a particular product. Then even if you just want to go 50 meters away, then also you have to pay this base rate. Okay, so we have to take this base rate into account. Then you have to also pay per kilometer rate plus per minute rate. Why? Because driver is investing his fuel plus his time in order to take you from source to destination. That's the reason why all these three parameters would be added in order to get the base fare. Okay. Now coming back to this pricing strategy, once we have calculated the base fare for the specific product, we have to also use the pricing strategy. Why? Because let's say currently it's the night time. So in that case, whatever base fare we have calculated, we have to add some amount extra in that, isn't it? So that's the reason why we have to first calculate the base fare, then use the pricing strategy in order to calculate extra money which we have to charge to the rider. So there can be various types of pricing strategy. One is night based, second is location based, and there can be many more. Okay. So this is how we calculate the fare. Okay. And finally, we save that fare into the fare database. So for the database, I am using this in-memory hash map. And one more thing that I am doing is I am saving that fare for exactly TTL seconds. After that, if you try to access that fare ID, it would say that it is expired. I'll be directly showing this thing in the code section. Okay. Now let's see other classes. So yeah. So in the ride service, we have a function called as request a ride. So this function will be assigning a driver to the rider. So for that, we need to provide the fare ID and the product which we selected, also the source and the destination location. Okay. So this particular ride will first check whether the fare is expired or not. If it is not expired, then it will interact with the driver matching service, and this driver matching service will first get all the nearby drivers within a specific radius and then use driver matching strategy in order to assign a specific driver. So currently we are using two driver matching strategies. First is highest rated and the second is nearest driver. Okay. So on the basis of that, we would be assigning a driver to a specific rider, and then we would be returning the ride object. So we have already seen the ride object, right? So with this, we have seen all the entities present in our design, and we have also seen the flow of those three functions which we have to implement. All right. Now let's check out the output of this system. Now before checking out the output, let's try to understand how exactly Uber calculates the shortest distance and the minimum time to reach the destination. All right. So firstly, this is the map which is generally shown to the end user, isn't it? So what Uber does is Uber first converts this map into a graph. So if you are familiar with the graph data structure, then you would be knowing that a graph has total three things. The first is the node, second is the edge, and the third is the weight on that edge, isn't it? So in this map, what they do is they take the intersection of the roads and represent that as the node. Okay. And the road itself acts as the edge. So let's see that. So this is how they create the graph, wherein the node is the intersection of the roads and the edge is the road itself. And further, this edge would be a directed edge. All right. Because the road can only go in some direction, right? It can be unidirectional or it can be bidirectional. So that's the reason why we would be having a directed graph. Apart from that, each and every road would have certain weight. All right. So if you are trying to calculate the distance, then in that case, the weight would represent as the length of the road in the meters. And if you are trying to calculate the time, then in that case, it would be seconds. Okay. Now let's assume that the road which is over here has lots of traffics, and that's the reason why the time it takes from going from one node to another node is 200 seconds. Now after a few minutes, if the traffic on this road decreases, then in that case the weight will also decrease, right? So Uber updates the weight in real time based on various traffic signals. All right. So I hope you have understood one thing, that is Uber converts the map into a directed graph wherein each and every edge would be having a weight. Now let's assume that this is a graph of the entire world. All right. So since this is a graph of entire world, obviously it would be having billions and billions of nodes, probably trillions, right? So if I ask you to find the minimum time it would take from source to destination, then obviously one algorithm that would come into your mind is Dijkstra's algorithm, right? But the problem over here is, since this graph has lots of nodes, the Dijkstra's algorithm will be inefficient because the time complexity of Dijkstra's algorithm is E log V. All right. So what Uber did was, instead of using Dijkstra's algorithm, they started using A star algorithm. All right. Now, if you are not aware about A star algorithm, then in simpler words, A star algorithm is nothing but the Dijkstra's algorithm plus it would have its own brain. Why am I saying that? Because see, if you are using the Dijkstra's algorithm from the source node, then this Dijkstra's algorithm will go in all the four directions. That is, it will explore all the nodes around it. But on the other hand, if you are using the A star algorithm from this source node, then it will directly go in the direction where destination is present. So it will start going in this direction. All right. So that's the reason why they started using A star algorithm. And for most of the cases, it was working efficiently. Why? Because most of the people just travel at smaller distance, but still some people would be traveling longer distance, right? And for the longer distance, A star algorithm was not working efficiently. Why? Because let's say you have to travel hundreds of kilometers. All right. So between the source and the destination, there would be millions of nodes, isn't it? And since it would be having millions of nodes, the A star algorithm will also work inefficiently in that case, right? So now the goal for Uber was to make this A star algorithm efficient for the longer trips as well. All right. So what they did was they thought about pre-computation. All right. Now, if you are pre-computing this entire graph, then you would be able to go to the destination in, let's say, O of 1 time only, isn't it? But the problem over here is, let's say currently the traffic on this road is very less, and that's the reason why the weight is also less, right? But if the traffic on this particular road increases, then the weight will also increase. And since the weight is changing, you have to perform that pre-computation again, right? And it would be inefficient because this graph has billions and billions of nodes since it represents the entire world, isn't it? So that's the reason why we cannot pre-compute on this entire graph. So the second thought which came into Uber's mind is, why not divide this big graph into smaller chunks? So that is what they did. They divided the entire world into smaller chunks, wherein each of this chunk or each of this partition will only have couple of thousands of nodes. Let's say this has 5,000 nodes, this has 4,000 nodes, and so on and so forth, right? Now they can easily perform pre-computation on this step. So each and every node in this particular partition would be having the data. By data, I mean that each and every node would be knowing what is the shortest distance and what is the minimum time to reach all the boundary nodes. Okay. So this node would be knowing what is the minimum time it would take to reach this node and this node and this node and so on and so forth, right? Similarly, this boundary node will also know what is the minimum time to reach all the other boundary nodes, right? Now, one cool part over here is, even if let's say the weight on this particular road changes, then you have to perform pre-computation, right? And that pre-computation is also efficient because you have to perform that pre-computation step only on the smaller graph, not on the entire graph which represents the world, right? So that's the reason why pre-computation step has now become efficient. Okay. And since pre-computation step has become efficient, A star algorithm has also become efficient for longer trips. Why? Because let's say I want to go from this source to this destination. Okay. So A star algorithm will first go to this boundary node, and from this boundary node, it will directly jump to this node. Why? Because it already has the information which is pre-computed, isn't it? That is, this black node will know the minimum time it would take to reach other black nodes. All right. So from this node, it would directly go to this node, and then this node. So this is how Uber calculates the duration as well as the distance. All right. So that is what I have written over here. And one more thing is, they also use something called as DeepETA. So till now, whatever we did was nothing but the function which would be executed by the routing engine. All right. So this routing engine will be providing the minimum distance as well as the ETA. All right. And this ETA was accurate, but Uber was not satisfied with this. Uber wanted to make this ETA highly accurate. So in order to do that, they started using DeepETA. Now, what is the DeepETA? So DeepETA is nothing but a post-processing model. That is, first you have to calculate the ETA using the routing engine, which we saw just now. After that, whatever ETA you are getting as the output is then given to the machine learning models. All right. So this particular machine learning model will basically calculate the difference between the ETA which is computed by the routing engine and the real world observed outcomes. On this basis, they will get the difference. And further, this is the difference which is added to the ETA of the routing engine. All right. They are adding this delta to the routing engine's ETA in order to make it highly accurate so that they can adjust the ETA from the routing engine and the real world observed outcomes. All right. So this is the post processing step done after the routing engine part. Okay. And finally, whatever ETA they are computing is being used by various services of Uber, like Uber Pool and Uber Eats, right? So I hope now you understood both the steps, that is routing engine and the DeepETA. So this is how they exactly calculate the ETA and the distance from source to destination. So now we'll be seeing total 4 demos. The first one is to get the fair estimates of all the products. So assume that you are currently on this screen and you enter the source and the destination location, right? So what will happen under the hood is it will call this function called as get fair estimates, and the source and the destination would be passed over there. Okay, on the basis of that you would be getting the product to price mapping, right? So basically you will be shown this particular stuff wherein each product would be on the left side and the price would be on the right side. Done. Now in demo 2 I would be successful in booking the ride because I'll be trying to book that ride within the TTL, right? So in order to do that, I'll have to first create the fare. That is, I have to first select a particular vehicle and go to the next page. And on the next page, we will be requesting a ride. Okay. So in this function, we have to pass a product and the source and the destination location, right? And once a fare object is created, we have to pass the ID of that fare object and the product and the source and the destination in the request ride function, right? So over here, the booking would be successful. But in the demo 3, the booking would be failed. Why? Because I would be booking after the TTL. So currently in my system, the fare object would be expired after 5 seconds. So in order to simulate this demo 3, I am making this thread slip for exactly 6 seconds. It means that at this time, the fare object would be expired. So if I give the ID of the expired fare object, I won't be able to request a ride, isn't it? So appropriate message would be shown over here. And in the demo 4, what I've done is I have one driver in a region, only one driver, and there are 2 riders who are trying to book a ride. Okay, it means that this driver should be assigned to exactly one rider, isn't it? So that is what I am trying to simulate over here. So both of them would first select a product and both of them will simultaneously try to request a ride, and only one of them would be successful over here. So now let's see the output of all the demos. First, let's wait for demo 3 to be completed. Okay, so in the demo 1, we should be getting the product to price mapping, right? So this is that thing. Here all the products are listed and their price are shown adjacent to that product. Okay, and by the way, you can round off this stuff if you want. In the demo 2, I would be successful in booking the ride. Why? Because we are trying to book that ride within the TTL. So that successful message has been shown over here and driver 2 has been assigned to us. Okay. And in the demo 3, our booking would be failed. Why? Because obviously we are trying to book after the TTL. So that message has been shown to the user. And in the demo 4, 2 riders are competing to book one driver, right? So only one of them is successful. The other one has failed. So I hope now you understood all the 4 demos. Now let's check out the code. So over here we would be having different packages like enums, models, repositories, services, and strategy. And we have already seen the models and the enums in the class diagram, right? So we'll just focus on the service, strategy, and the repository. So let's start with the service. So first is the driver service. This driver service will be interacting with the driver repository in order to perform the CRUD operation on the in-memory database. All right. So in this service, we will be having the register driver function, which would be basically registering the driver. And we would also have the update location function. Here we'll be first checking whether this driver is present or not. If this driver is not present in the in-memory database, then we'll be throwing this exception, as we'll be just updating the current location. Now coming to the rider service, the rider service will also have the register driver function and get rider by ID function. So over here we will be fetching the rider from the in-memory database, and if the rider is not present, then we'll be throwing this exception as we just written the rider. Now let's check out the fare estimation service. So in this service, we have two main functions. The first one is to get fare estimates and the second one is to create fare. So let's check out this function first. So in order to get the fare estimates, we have to first calculate the distance from source to destination and duration from source to destination, right? So we have already seen that Uber uses the routing engine in order to compute both of these parameters. But I have just used the normal Euclidean formula, which would look something like this. All right. So using the Euclidean formula, I'll be getting the distance, and for 1 kilometer, I'm saying that I will be taking 2 minutes. All right. So this is how I'm computing the distance and the duration. Now for each product, I am getting the base fare using this formula. The formula is very simple, wherein we are just adding the base rate and the per kilometer rate and per minute rate. So using these three parameters, I'll be getting the base fare of a specific product. Now, once I get the base fare, I'll be using the pricing strategy in order to compute the surge in that base fare. So let's say if the current time is the night time, then obviously we'll be charging some extra money from the customer, right? So for that, I'll be using this night pricing strategy, wherein I'll be checking whether the current time is between 10 p.m. and the 6 a.m. If it is so, then I'll be returning 50, indicating that rider should be charged 50 rupees extra. Okay. So on top of that, we would be charging this much amount from the rider. So I'm adding that to the base fare. And finally, I'm adding the entry into the hash map so that I can show the hash map to the end user. All right. So this was the get fare estimate. Now let's check out the create fare function. So in the create fare function also, we have the same logic where we first calculate the distance and then duration, and based on these three parameters we would be computing the base fare, and then we'll be using the pricing strategy to compute the surge amount. Okay. Now after all this stuff, we are creating the fare object, and after creation of this fare object, I am saving that fare object into the in-memory fare database using the fare repository, and this fare object would be expired after 5 seconds. Okay, so let's check out this stuff first. So in the fare repository, I have one class which is fare entry. This particular class has three attributes. The first one is the rider ID. Basically, this is the ID of the rider who has created the fare object. All right, and this is the fare object, and this is the expiry time. So after expiry time, this particular fare object is of no use. All right. So I have this in-memory fare database wherein I'll be storing the fare ID and the corresponding fare entry. All right. So coming to the save function over here, what I'm doing is I am saving this particular fare object into the in-memory hash map, wherein the key is the fare ID and the value is the fare entry. And before creating this fare entry, I am calculating the expiry time. So expiry time would be the current time plus the TTL. So TTL is 5 seconds, right? So this would be the expiry time. And whenever we call the get fare function, that time I'll be fetching the fare ID from the in-memory hash map, and I'll be checking whether the entry is null or not. If it is null, or if the fare is expired, in that case I'll be returning null. And I'll be also checking whether the fare object is created by this rider or not, just for the security reason. So if the fare object is not created by this rider, then in that case also I'll be returning null. And if all these conditions are false, then in that case I'll be returning the actual fare object. All right. And one more thing that I'm doing is I'm using this scheduled executor service. So in this scheduled executor service, I will be executing this function after every 1 minute. All right. So what this function does is it will go through this entire in-memory hash map and remove all the entries which are expired. All right. So this is what this particular cleaner will do. Right. Now coming back to the fare estimation service. So we'll be saving that into the in-memory database, and after that we'll be returning the fare object. So this is how we create the fare. So with this we have seen two main functions. The first one is get fare estimate and the second one is create fare. Now let's check out the third main function, which is request a ride, and that function would be present in the ride service. So in this ride service we have this function called as request ride. Here we'll first check whether the fare object is expired or not. If it is expired, then we'll throw the exception. If it is not, then in that case I'll create the ride object, and I'll also try to find a nearby driver. So in order to do that, I have this driver matching service which will help me to find the driver. Okay, so let's check out this driver matching service. So in the driver matching service, there's a function called as find driver. In this function, we'll be first fetching all the nearby drivers. Okay, so that will be done by the function which is present in the driver repository. So in the driver repository, I'll be going through each and every drivers, and I'll be checking whether that driver is available or not. And if that driver is available, then I'll be checking the distance. And if let's say the distance is also valid, then I'll be collecting that driver into a list. So all the drivers would be collected into a list, and finally I'll be returning that list of drivers. All right. Now currently I'm finding the nearby drivers using this stuff, but in reality we won't be using this stuff. Instead, we would be using some index. So let's check out that. So there is something called as geospatial indexes, which are efficient for searching anything based on location. All right. And this geospatial indexes has various algorithms. One famous algorithm is GeoHashing. So one thing that I want to highlight over here is if you try to search the nearby drivers based on two-dimension data like latitude and longitude, then it would be inefficient. So in order to make that efficient, we have to convert that two-dimension data into one dimension. So what we generally do is we hash that two-dimension data so that we can get one single string. All right. So we are calling that string as GeoHash. Now the length of this GeoHash can range from 1 to 12. 12 length GeoHash basically represents your exact location, whereas 1 length GeoHash represents the entire world. All right. So now let's try to visualize this stuff by going to this website. So currently on this website, we can write any latitude and longitude, and we can select the length of the GeoHash. So for example, I have selected the length as 5. So it is basically showing this entire area. Now, if I try to increase the length of the GeoHash, it will show me the exact location of this latitude and longitude. All right. So in the database, what I'll be doing is I'll be storing the exact location of all the drivers. Then all the drivers who has this prefix will be present in this particular area. All right. So in this area, all the drivers would be sharing this GeoHash as the prefix. So if you want to find all the drivers within this area, you can just query the drivers based on this particular prefix. And if you want to know what is the area of this box, then there's one table which is given to us. You can check out this table as well. And the cool part over here is the Redis has the inbuilt support for the geospatial indexing. Alright, so you can have this geoadd and geosearch command. So as you can see over here, we are able to find all the locations within the 5-kilometer radius. Now, one more nice thing about this is you have different shapes. One is circle and the second is box, right? So you can go through this Redis commands. I'll be giving the link of this website. Now let's get back to the code. So once we get all the nearby drivers, we have to filter those drivers based on the product. Because some of the driver would be providing Uber XL service, some would be providing Uber Auto service, etc. Right? So I need to filter the drivers based on the product which the rider wants, right? So this is how I would be filtering the drivers based on the product. And after that, I am using the driver matching strategy in order to get the specific driver among the filtered drivers. All right. Now I have two types of driver matching strategy. The first is highest rated driver and the second is nearest driver. So let's check out both of them. So in the highest rated driver, what I'll be doing is I'll be sorting these available drivers based on the rating. Okay, so we'll sort that in the descending order. And finally, I am looping through all the available drivers and assigning one of the driver atomically. So what I mean by atomic is, so let's assume that there are two riders, okay, and only one driver is available in that location. So what will happen is both of the threads will be starting the for loop. So they will simultaneously go into this for loop and they both of them will be trying to get this driver. All right. So they will be calling this function, which is mark unavailable. But the thing is, this mark unavailable function is atomic in nature. That is, it is using this compare and set technique in order to convert this Boolean variable from true to false. And only one thread will be successful in doing that, even if both of the thread is simultaneously calling this function, right? So only one of the thread will be successful. Let's say T1 is successful. So T1 goes inside this, and this is the driver which is assigned to thread T1. T2 basically goes over here. That is, it will go to the next driver and try to get that driver. Okay. So this is how the concurrency part is handled. Okay. So this was the highest rated driver strategy. Now we also have this nearest driver matching strategy. So here I am sorting these available drivers based on the current location. All right. And after that, I am repeating the same logic. Now coming back to the driver matching service. Here, once I get the driver from the driver matching strategy, I am returning that to the write service. All right. So write service will get that driver and that driver would be updated into this ride object. All right. And that driver will also have some vehicle, isn't it? So that vehicle is also updated into this ride object. And finally, I am saving that ride into the in-memory ride database. So we would be saving this ride object into this in-memory ride database using this CRUD operation, which is present in the ride repository. All right. So this is how we book a particular ride. Okay. So with this, we have seen all the services, all the strategies and the repositories. So I hope now you understood the entire ride sharing system. If you did, then please like the video and share this with your friends. Thanks for watching.